Hello students, welcome to Sorosha classes. In today's lecture, we are going to discuss the factors on which the delta O value depends. So for this, I've kept this table for you, as you can see over here, this one, and we're going to take some help from this table. So point number one is the delta O value increases as the oxidation state, or one can say primary valence of metal ion increases. We know delta O, which is nothing but energy splitting parameter of a octahedral field, will be proportional to h nu lambda, or it can be said also h nu, or it can be said also hc by lambda per atom. Okay, I'm saying. Per ion will be better, right? Isn't it? Per ion. Okay. Now, as we can see that delta O is directly proportional to nu bar. And we know the nu bar is given in centimeter inverse. So let us compare, okay? As we can see, hexa aqua vanadium 3, its delta O value is higher than the hexa aqua vanadium 2. So oxidation state 3 value of delta O is higher. So in that sense, we will say, as for example, delta O of complex, this one is greater than that of VH2O 2 plus. So if we were to think about a case in which we are comparing the delta O values of FeH2O whole 6 3 plus and FeH2O whole 6 2 plus, with the above given logic, this will be greater. Is it so? Well, as you can see, it is indeed higher than that of the, so plus 3, that is hexa aqua iron 3, is greater than that of the hexa aqua iron 2. Again, if we check a few more, say delta O of cobalt H2O whole 6 3 plus is compared with hexa aqua cobalt 2. There also we see that the value of the cobalt complex, which is having higher oxidation state, is greater than the one which is having lower oxidation state. One can also think of the hexa aqua, hexa ammonia cobalt 3 and hexa ammonia cobalt 2. There also we can see whenever the oxidation state of cobalt is lower, okay, we are having lower delta O value. Similarly, you can also compare FeCN6 3 minus, which means it is higher oxidation state, that is iron is in +3 oxidation state with FeCN6 4 minus, which means iron is in +2 oxidation state. There also, whenever the oxidation state is lower, the delta O value is lower. So also is the wave number. Okay. Now, if we were to compare a triad, okay, for a triad of periodic table, what do we find? On comparing the delta O values of its complexes with same ligand, delta O value increases down the group. Now, what it means? Suppose I was comparing IRCl6 3 minus with RHCl6 3 minus with COCl6 3 minus. Suppose I was comparing the delta O values of these, then that will be higher than that, than this. Similarly, for a OSH2O whole 6, 3 plus will be higher than that of the RuH2O whole 6, 3 plus than that of the FeH2O whole 6, 3 plus. Now, why this is happening? The reason we give is that as the size of d orbital increases, the energy gap, that is delta O, increases. So we can also say that down the group, okay, pairing of electrons is more allowed. In other sense, high spin complexes down the group become low spin complexes. Obviously in triad. Okay. Because the size of the d orbitals increases, so pairing of electrons becomes more allowed. So if, say, a cobalt complex with any ligand, it is high spin, but if you go to the iridium complex with the same ligand, it will become low spin, okay, and not be high spin. So these abnormalities are observed, okay, because the spin pairing being allowed. Now the other one that is critical over here, which is our point C, also known as the spectrochemical series, which is basically arranging complexes, okay, according to the energy splitting that is observed when the ligand changes. Okay. So spectrochemical series is the arrangement of ligands in the order of increasing over here actually the octahedral splitting parameter. So over here iodine is our weak field ligand. Okay. So we start with iodine, bromine. Now over here NCS is the over here ambident ligand and S over here is the donor point. Then we have chlorine, fluorine, OH, oxalate, which is almost similar to that of the water. Then we have NCS, NH3, ethylene diamine, bipyridine means BPY, phenolphthalein. Then we have the cyanide, and then which is almost similar to that of the carbonyl, which is a strong field ligand. Okay. So once we go from a weak field ligand to a strong field ligand, our octahedral splitting parameter keeps increasing. Okay. So looking at two different complexes of the same metal but having two different ligands and judging its ligand field strength, one can conclude which will be having a higher value of octahedral splitting. Okay. Now, instead of remembering this whole series, I am summarizing and giving you a hint in which I am saying that halide donors have less energy, followed by O donors. Okay. Then we have the N donors, and then we have the C donors. You can generalize this even better by saying group 17, okay, A donors, followed by group 16 A donors, followed by 15 A donors, followed by 14 A donors. I think that will make it more general for students who are appearing for GET, NET or IIT JAM exams. So let's compare now. Okay. So we know that O donors have lesser energy than the N donors. So if you're comparing the, so let me erase this part now so that we can compare. Yeah, I'm erasing this. So let's compare hexaqua nickel 2 complex with the hexa ammonia nickel 2 complex with the tris ethylene diamine nickel 2 complex. And as you can see, from water to ammonia to En, the according to the spectrochemical series, the ligand field strength increases. So what we will see that it is lower for nickel OH whole 6 2 plus, which is lower than that of the next complex, which is Ni NH3 whole 6 2 plus, which is less than the Ni En whole thrice 2 plus. Okay, as you can see over here. Again, one can compare over here, say iron FeOH 2 whole 6 3 plus with FeOX whole thrice 3 minus with FeCN whole 6 3 minus. In all these, iron is in plus 3 oxidation state, and we know from the spectrochemical series that, as you can see, water and OX are pretty much similar. Okay, but bidentate ligands will give more stability, so that is something known as chelate effect. We will study later on. So OX will be having higher value than that of the iron 3 hexaqua complex, and as you can see at the end we have over here the CN, right? So it is basically, if we compare now, we will say FeOH2 whole 6 3 plus less than FeOX whole thrice 3 minus. This difference is because of chelate effect, because OX, that is oxalato, is a bidentate ligand, and then we have FeCN whole 6 3 minus. If we compare another one, okay, let's do that. Let us compare, see, chromium hexaqua complex in the plus 3 oxidation state, chromium hexammonia complex in the plus 3 oxidation state, chromium hexacyano complex in the plus 3 oxidation state. Again, from O to ammonia to CN, the value is increasing. Okay, which proves again that the spectrochemical series is correct. Okay, so this is our points regarding the delta O. One last point that we would like to mention, that the delta O value also depends on the coordination number. That means octahedral complexes splitting is more than that of the tetrahedral complexes. In fact, delta T is equal to 4 by 9 delta O, that is the expression. So one can say, in fact, delta T is almost half of delta O. So these are the factors on which the splitting energy of octahedral complexes depend, and we have given one relationship, that is how the tetrahedral field splitting is related to the octahedral field splitting. Thanks for listening. Keep visiting Saraswati classes for more in-depth analysis, okay, of coordination chemistry. Thanks for listening. Have a great day.